Excuse me. Okay. Today we're going to talk about the Henderson-Hasselbalch equation in more detail. We're going to use it to solve problems to understand this idea of a buffer and to explore more how biochemical reactions actually behave in vivo, in real cells. Okay, so let's start with a redefinition of the term buffer. At the beginning of the semester, I may have mentioned to you this Professor Good, who was a biochemist that came up with a list of buffers that work really well in enzymatic reactions, reactions that are often encountered in biochemistry. So what is a buffer? You know, this definition is very generic, but it's very useful, I think. Is a substance, quite often is a weak acid or a weak base, that can prevent changes in pH from taking place too quickly. And by too quickly, I mean not necessarily time, but when conditions, chemical conditions change. So for instance, if you have a solution of a buffer because you made it for a particular study, and in that study that you're conducting, the reaction results in a slight increase of the concentration of protons, H pluses, or a slight decrease of the concentration of protons. Well, you don't want the pH to change abruptly. So the buffer is going to absorb some of those extra protons or release some protons to prevent the pH from fluctuating too much. So in essence, that's what a buffer is going to do. It's going to pick up or release protons to keep the pH from changing drastically. Now, buffers are chemicals. They're not thinking entities. It's not like they're thinking, oh, I'm going to keep the pH here. No, they do so by a chemical reaction. And in a future lab, you're going to explore that chemical reaction as something called a titration curve. In a titration curve, you may have learned in general chemistry, you take an acid, and to that acid you add a base, and then you record the changes in pH as time goes by, and as the addition of this acid or base increases. And you actually plot that information onto a graph, which in the end is called the titration curve. We're going to look at some titration curves either today or next week. But suffice to say that a buffer is what I just described, a substance that keeps the pH from changing too drastically. Now, obviously, you have different situations in which you need to keep the pH at a certain range. And your choice of buffer is going to be based on a property of the substance known as the dissociation constant. Now, we looked at a dissociation constant before, bless you, we call it the Kw, but every acid, every weak acid and every weak base has a dissociation constant that describes that particular substance. Now, hydrochloric acid does not have a dissociation constant because, as you know, it's a strong acid, and that means that if you put hydrochloric acid in aqueous solution, there is no equilibrium. At equilibrium, rather, all of the hydrochloric acid has become the products that you see here. So there's no dissociation constant that we can find. It doesn't exist. Now, for a generic weak acid, and let's just call it HA, there is a dissociation constant unique to that particular acid. So the weak acid breaks apart into protons and the conjugate base. So this is a name that you need to remember. And this happens in a very defined chemical equilibrium. Now, when you take the ratio of the products to the reactants, you come up with this so-called dissociation constant. So, for instance, in this particular example, I can write an expression for the dissociation constant that is going to look like this. The product of the products divided by the amount of the reactant or reactants. In this case, there's only one. Now, keep in mind that this is all happening in water. So this is all aqueous. Now, just as we define the Kw as the dissociation constant of water, we're going to define the dissociation constant of different acids as having a constant value. And then, more than that, we're going to calculate something called the pKa, the dissociation constant expressed in terms of logarithm. Okay? So we're going to get there very quickly by rewriting the equation for pH, but this time using K instead of H. And it's going to be the negative log of the Ka. I was looking at your book, and sometimes they use actually the following equation, which is the same thing. So they apply the rules of logarithms, and instead of putting the negative sign here, they just take the reciprocal of that and express it like that. It's the same thing. I'm so used to the negative log of that I keep using it, but just keep in mind that that's the same thing. Now, in general, the smaller the value of the pKa, the stronger the acid. Okay? By the same token, the larger the Ka, the stronger the acid. Now, as I mentioned a few minutes ago, phosphoric acid is a great example of how this actually works. And I like phosphoric acid because it has not one, not two, but 3 Kas. So let's take a look at that one. And with that, I'm going to try to explain these different situations. Remember, the Ka is always defined as the ratio of the products to the reactants. Any questions? So here we go with phosphoric acid. It actually can be used as a buffer. It's not commonly used as a buffer, but it can. So I'm going to start on the left. I hope I can write it here because I am intending to record this thing. I apologize to those of you who are way over there and may not be clearly seeing my screen, but I need to confine to this just because of that recording. So here we go. H3PO4 is the structure, the chemical formula of phosphoric acid in its natural state. Now when you put this in water, this actually yields a proton. And then the other product is going to be simply this with one less hydrogen and a negative charge. So it's going to be H2PO4 1 minus. Now this has a dissociation constant of 6.9 times 10 to the negative 3. Okay? Now, this conjugate base, that's the term that we're going to keep using when we have a dissociation, has 2 more protons that can be removed, or that can be lost, if you will. So there's another dissociation constant. I better start writing those things a little bit smaller, or I'm going to run out of room. And as you can imagine, we're going to remove a hydrogen from here. We're going to have it as a product. And the conjugate base now becomes HPO4. We're going to increase the charge by 1 negative more because it lost another positive charge. So now this has a charge of 2 minus. Not terribly important, but it does distinguish the 2 species from each other. And this has a different Ka. That value, according to my screen here, is 6.2 times 10 to a negative 8. Okay, we'll talk about these values in a minute. Let's just finish with these. There's 1 more proton that can be removed. We increase the charge of the conjugate base by 1 more, so it's 3 minus. And the Ka, I'm going to look it up, but if the first one was 10 to a negative 3, the second one is 10 to a negative 8, seems to be going down, I mean up in the size, but it's actually a smaller number. This is probably going to be the smallest of the 3. And according to my table, is 4.8 times 10 to a negative 13. Okay. Now, so we need to be very good at calculating. And I'm going to calculate this one for you, but then please calculate these 2 yourselves. So what we're going to do is we're going to use this formula to calculate the pKa of the first dissociation, the first proton of phosphoric acid. So what is the negative log of 6.9 times 10 to a negative 3? So I have a calculator here. And I come up with 2.16. Are you guys in agreement, or you just believe in my calculation? It is, somewhat important that you guys at least know how to ask your phone or your speaker at home, get me the negative log of this value. I'm not expecting you guys to use calculators anymore. You can certainly use ChatGPT, whatever you want, but you do have to be able to make that conversion. Yes?
For the proton, for PO4, do you have to put a coefficient in the proton, like 3H plus?
Oh, no, not really, because that's a very, very good question. Each proton is already accounting for the previous one.
Okay.
In other words, so if we count these 3 right here at the beginning, we have 1, 2, 3 total. So we remove 1 at a time. Very good question, my goodness. Another way of putting it is, if you add this to that, that gives you 3, but that doesn't work for this. So 1, 2, plus I guess the one over here is the third one. Very good question, though. Molar-wise, it is as written here. You produce 1 mole of this and 1 mole of this. And then you produce 1 mole of that and 1 mole of that. And that's actually a very important point to understand, because we're going to be using molar concentration later. Okay, so what about the second pKa? I'm going to cheat and just look at the table. So phosphoric acid, the second one is 7.21. And the third one, 12.32. Now, that question about the numbers, that's actually, it got me to some degree, because when we write the pKa's, we do have to put the subscript on that. If that's what you meant, yeah, I stand corrected. So definitely, we had to put pKa1, pKa2, and pKa3. Absolutely, if that's what you meant. Okay. Okay, yes. Otherwise, we don't know which one is which. Very good point. So pKa1 is the first proton that was donated, pKa2 the second proton, pKa3 the third one that was still there. And then you have a conjugate base with nothing else. Now here comes the stuff that sometimes I wish books would just tell you up front some of these things instead of you having to make the connections. Now, the very first thing, a substance can be a buffer, ideally 1 pH unit plus minus away from the pKa. In other words, if I wanted to use phosphoric acid as a buffer, I better want the pH to remain constant around 2, because this guy will only work as a buffer around pH 2. So what I'm basically saying is that a buffer is going to be a working buffer plus minus 1 pH units from the pKa. In reality, that's a little bit too strict, so we go all the way to 2. Plus or minus 2 pH units from the pKa. So to use the second pKa as an example, if you want to keep this reaction where you're using this buffer at around a pH of 7, that will actually work until the pH drops below 5 or drops or increases above 9. Does that make sense? So 1 pH unit away from this is perfect. 2 pH units away from this is becoming really not very good anymore. It's still buffering, but after that, the change on pH is going to be so drastic that it's going to ruin your reaction. So you cannot afford to add that much acid or that much base if you are keeping the pH around 7 because of that buffering capacity being limited by the 2 pH units that I just mentioned. Okay, so let me add one structure to the bottom of this drawing to ask you a hypothetical question before we start making calculations with Henderson-Hasselbalch. Excuse me. So this is our very first look at a very special type of molecule in biochemistry that is composed of carbon, more carbon, some nitrogen, and to make it simple, I'm going to use this example in which there's actually 2 hydrogens on that carbon. Any idea where I'm going with that? This is the topic of essentially the next chapter. So you have a nitrogen connected to a carbon connected to another carbon. Now, not fair because I haven't given you enough information, but let me provide you with more information. So let's add an oxygen and an OH to that end, and then a hydrogen and a hydrogen to this end. So in the review for this course, some of the functional groups that you needed to remember were the amino group and the carboxyl group, which is an acid. This is an acid because of that hydrogen. So now if you're guessing amino acid, that's exactly right. This is the basic structure of an amino acid. In particular, this is glycine, the simplest of all amino acids, where the changing group that you find in one of the 20 amino acids is hydrogen, instead of a methyl or a phenyl or other functional groups. Now, the reason why I have here glycine is because I want you to realize that there are 2 ionizable groups here. So you have this acid, and then you have this base. It turns out that each of them has a Ka value, and it has a pKa. I need to look it up. I never memorize these things. So let me look at the Ka values of glycine. And in fact, I'm just going to give you the pKa values. So this guy right here has a pKa value of, according to this site, which is Pearson, 2.34. Ergo the acid, right? This other ionizable group has a pKa value of 9.60. Ergo the base, or therefore the base. You should be thinking, wow, this guy can actually hydrogen bond. This guy can hydrogen bond. True. So that's why amino acids are actually quite soluble in water. Now, unfortunately, I say unfortunately because it complicates matters, this hydrogen is not always a hydrogen, it can be other things. So that other things may or may not have a pKa value. So some amino acids have more than 2 pKa's, but all amino acids have at least 2 pKa's. One for the acid and one for the base. So here comes the question that I have for you to see if my drawing over here made any sense. And let me, of course, give you a big clue. Most books in the past, I haven't checked books of biochemistry recently, certainly not of biology, write the chemical formula of amino acids incorrectly. That structure that I have here does not exist. It cannot exist. And it cannot exist because of what we just said, the pKa values. So at pH 7, physiological pH, what would you think is the structure of this amino acid? And let's work out the answer to my question together. Let's take a look at this guy first. We need to look at them independently. That was one of the difficulties on that problem that one of your classmates asked me about. When you look at this chemical formula, you have to realize that you have two things going on at the same time. Two different equilibria taking place at the same time. One is here, and then there's a different action over here. So let's take a look at what happens here at a pH of 7. We can actually isolate that and then just look at that as an acid-base equilibrium. I'm going to have to do it over here. That's not a problem. So that's a covalent bond. I wrote it backwards. I put the proton second. But this is actually the equilibrium of that amino group. We have a pKa of 9.6 for that equilibrium. So this has a pKa of 9.6. So my question is, at pH of 7, what do you have more, that or that? The left or the right at pH 7? You need to be careful because you pointed to the right direction. So let's identify the acid and the conjugate base, okay? So that we can relate it to this. So in this drawing, if we ignore the rest, this is the acid and this is the conjugate base, right? And here is the pKa. So over here, this is the acid and this is the conjugate base. The base that results from the loss of that proton. So I removed that one hydrogen extra. I ended up with that. That is happening in an equilibrium that at pH of 9.6 is right in the middle. 50% is that, 50% is that. But if we move to a lower pH, the lower pH is going to favor the acid, right? There's going to be more protons, so there's going to be more of a chance of that proton not wanting to leave because there's plenty of protons, so they're grabbing them. So at a pH of 7, we're way 2 units away from these, we're going to have almost 100% of that and almost 0 of that. So if I want to write this structure correctly at pH of 7, I need to add a hydrogen and a plus sign here. That's really what happens at physiological pH. You don't have NH2. You have NH3+. Super important that you realize that. And most drawings, I mean, if we pick them randomly, they're going to be wrong. So let's do it for the carboxyl group. And I guess I'm going to use the same notation. So we have COOH, and if we remove this proton, we have COO minus. So the acid, COOH, the base, COO minus 1 plus the proton. What's the pKa according to my drawing here? 2.34. So, by the same analogy as before, at a pH of 2.34, you have 50% of the acid in this form, well, 50% of the species of the amino acid, the group, the functional group, and 50% in this form at a pH of 2.34. At a pH of 7, which is higher than 2.34, we're going to be here mostly, almost none, if not zero, is going to be this. So the right formula for this would be like that. So at physiological pH, at a pH of 7, this is what exists for glycine, not the stuff that I had. Let me turn on the projector just briefly, just to review a few entries. I'm now just curious, but that's the reality. And the explanation as to why is because of the pKa values of the two functional groups. Just give me a second here to connect to my PC. So that's the information that I was using on my explanation. And you know, interestingly, here they have very nicely that I don't even know what they're talking about, but they're mentioning 50% of that and 50% of that. So it must have something to do with what we were discussing before, different pHs. I don't want to even click there, but what I want to do is I want to see an amino acid table. So this is correct, right? Here we have the charged amino group, the charged carboxyl group. So what about that one again is just the wrong one. But here, I think they have it right. Again, I'm looking for glycine. Oops. So they seem to have it right. They have the plus and the minus. And I forgot to mention to you that this carbon right here is called the alpha carbon. It has a very particular denomination or naming. We'll explore that when we talk about amino acids and their structures. But anyway, my point was precisely that there's still errors made when this is written. Okay, so I'm going to copy this equation on the board so that we can start looking at it and prove some of the ideas that I have mentioned. So that's the so-called Henderson-Hasselbalch equation. One of the three topics that you have to really remember after you finish this course. If you don't remember the Henderson-Hasselbalch equation, and I don't mean memorizing the equation, but how to use it, then I really suck at my job, because this one is important. And by the way, I do forget that equation quite often. If I put my mind to it, I probably can rationalize the ratio, but I sometimes flip the conjugate base. I put it on the bottom, and the acid I put it on the top, and that's just, my brain sometimes playing tricks on me. So let me turn this off. I'm just going to put it on the board, and we're going to start using it. It's actually quite interesting how it works. So I'll put it on the left. If you're interested in how it was derived, there's explanations on YouTube on how you arrived to this equation. And it's actually quite entertaining to see, but I'm not going to. I want to remind you that this is a 200 level course, not a 300 level course. So we really want to emphasize the practical aspects of this equation more than how it was arrived to arithmetically or mathematically. So that's your Henderson-Hasselbalch equation. Now going back to my example over here of pH 9, my original example, because then I changed it to 7.21, and we'll do both. Now, you do have to do some thinking here, because if you were to put this equation and apply it to this, let's see what happens. Let's put it to the test. So we're going to say at pH of 9, how much H3PO4 is present. Now, I'm not giving you amounts. So that means we need to come up with at least a ratio, which is fine. So let's put numbers on the Henderson-Hasselbalch equation. So we have 9 is the pH equals the pKa that describes the phosphoric acid equilibrium is the 2.16, because there's no phosphoric acid here. There's only H2PO4 and only HPO4. So we need to look at this equilibrium. So we're going to put 2.16. I don't know where this is going to take us, by the way. Plus, I'm going to say log of x, because I didn't give you any amounts. So we're going to create it as a ratio. Now, if we solve for log of x, we have 9 minus 2.16 equals, I mean, this is the danger of using the Henderson-Hasselbalch equation incorrectly. I mean, we know we should not be here. We know at pH 9 we are somewhere over here. Let me see if I can get a calculator here. And I'll invite you to solve for x if you don't mind. It may take me longer than what it will take you. Essentially is 10 raised to whatever that difference is. I come up with a huge number. I don't know what you guys are getting. So a number that doesn't make any sense. So what happens if we fix it and we say now, okay, wait a minute, that doesn't work because really we should be using the Henderson-Hasselbalch equation in this equilibrium. And we cannot really answer that question numerically. So the conclusion is that there's virtually zero of that. Now let's ask the question more valid. We know that we are somewhere in here at pH 9. We're definitely not over here. So now I can ask the question of how much H2PO4 there is or how much HPO4 there is. And it's going to be in proportion. Remember what I said earlier. At a pH of 7.21, you're going to have 50% of that and 50% of that. If that's 0.1 molar, then you have 0.05 and 0.05. If it's 0.3, 0.15, 0.15. But now we are at pH of 9. So let's fix this to a reasonable entry. We are now at a pKa of 7.21. And let me just do the math here. 9. $1.79. Now let's make sure that I'm not making a mistake here as to how you come up with that. So log of x should be equal to 1.79. Am I right when I say x equals 10 raised to the 1.79? Yes, right? I mean, that's how you solve logarithms. Remember, I'm a biochemistry teacher, not a math teacher, so I forget my logarithm rules. So x equals 10 raised to the 1.79. So what is that numerically? Let's just do it. And I want to compare values because, oops, not like that. What? I think I know how to use this. I don't know why it's not letting me put the decimal point. What do you guys get when you raise 10 to the 1.79? I need two values that are the same so that we know we did it right.
I have 61.66.
61 point. 61.66. Anybody else? getting that? You got that? Okay, perfect. So now, let's see what that means. We have solved for x, but we know that x is this ratio, right? So let's put it here. This x is really a minus divided by HA. We have no values, we just want the ratio. Okay, so if I substitute that here, I have a minus divided by HA equals 60.166, right? Now, again, assuming that I remember my algebra, I'm going to move these, I'm going to solve for a minus by moving these to the other side. So I have 61.66 HA. Did I do it right? Algebraically speaking, I hope I did. So now, let me move it over here. A minus, let's take a look at where we are. Which one is A minus? This one, right? The HPO4 2 minus, this one. Which one is HA? This one. This is our acid. So this is the acid of this equilibrium. This is the conjugate base. So this is A minus. I'm going to say HPO4 2 minus equals 60.166, the concentration of this one. So what is that telling me? That I have, in proportions, 61.66 times more of this than of that at pH 9. Are you still with me? So we don't have numbers in molar amounts. We don't know how many moles, but we have them in proportion. If I give you actually a concentration, if I tell you, okay, we started with a 0.1 molar solution of phosphoric acid at this pH, you know that that plus that is going to have to total 0.1 molar. But that's another problem. We're not there yet. I just want to make sure that we understand what Henderson-Hasselbalch can do for you. And that is to predict ratios. So 61.66 times that amount is going to be equal that amount. Meaning you have that proportion. You have much more of these, 61.66 times more than of that at pH of 9. And that kind of makes sense because we are past that. We're past this equilibrium. Let's do it one more time to the second example that I mentioned to you, where I told you the answer was 50-50. Let's see if that is in fact the case. So any questions? Because I'm going to erase these and put new numbers, partially new numbers. So let me erase that, that. Now, we're going to pretend that we want to know how much of either of those two we have at a pH of 7.21. So now the pH equals the pKa. Okay? Henderson-Hasselbalch, pH equals pKa plus log of the ratio. This now is 7.21. Okay? That means if I solve for x, is log of x equals 7.21 minus 7.21, right? Which is 0. X then is 10 to the 0, right? Which basically means x equals 1. Now we go to the substitution of x by the ratio. So we are saying here that HPO4 2 minus equals 1 times H2PO4 negative minus. How did I get to that? Well, by doing the same thing that I did before. This is x. This time this equals 1. There's a line dividing this. A minus over HA equals 1. You solve for A minus, you have this result. You have A minus equal 1 times HA, which basically results into this. A minus is this one right here. HA is this one right here. We have nothing of that. We have nothing of that. I mean, we did get a number before. It was a huge number. So in the thousands and thousands. But this time we got a reasonable number. With pH 9 we got a reasonable number. As you can imagine, the closer you get to 7.21 in either direction, the closer this ratio is going to be to 1. Now, you can do more than that with Henderson-Hasselbalch. So let's do the next thing that we can do. Any questions before I erase this? Okay. Let's see if Henderson-Hasselbalch can help us calculate the pH if I give you the amounts of the two species. So now I'm going to tell you, you have a beaker here. Oops. In which we combine 0.04 molar H2PO4, 1 minus, and I add also 0.06 molar HPO4, 2 minus. So that's the mixture that I make in water. And I want to know the pH. So I need to realize that in that mixture I have no phosphoric acid and I have no phosphate. I only have these two, which are these two. So I know that the equilibrium that this is working at, the most that is happening in here is in this neighborhood, where the pKa is 7.21. But I don't know the pH, so we'll put Henderson-Hasselbalch. pH equals, according to that, is the pKa, so 7.21, plus the log of the ratio of the conjugate base to the acid. We need to pick right. This right here is a conjugate base, so that has to be on the top. And this down here is a conjugate acid, which is this one, so that has to go on the bottom. And then we'll do the arithmetic. So 0.06 divided by 0.04 And then I'm going to get the log of that. I get 0.18. So the pH of such solution is 7.39. That's when the proportion is, and check it out, 60% to 40%. I mean, this can be percentages. Would you agree that that's a fair statement? 60%, 40%? I mean, in this case, it was molar. And interestingly enough, it doesn't matter if I increase that tenfold. If this is 0.6 and this is 0.4, the ratio is still the same. And the pH doesn't change because it's the proportion of each other that is keeping the pH in that range. Okay, so those are two very straightforward examples of how to use Henderson-Hasselbalch. Sometimes it's not that clear. Sometimes the problems are a little bit more tricky, and you need to do a little bit more chemistry behind the scenes. So that's one of the problems in the homework that I probably should post that solution that I prepared for. I don't know if it was Isabel or her sister, but I did spend 5 minutes doing that for her. So I'll probably post it I'll send you an announcement with that, just in case some of you are encountering that situation. Okay. Boy, this felt like 2 hours to me, and it's only 1 hour. It's long, huh? Okay, I'm going to erase these, then I'm going to put some of the problems that I have prepared, and we can talk about any questions that you may have about the lab after that, but let me just, any questions? Okay. And sometimes it's how you read the question that may help you come up with an answer. Try to achieve. It's just not worth. Where is it? See, it's pending again, but it's there. I don't know why it's not synchronizing. And I already contacted technical support. Okay, let's preview as a student. So this is the assignment that is not graded, but that I want to use for making sure that we understand all of these ideas in this chapter. So let me go take a quick drink of water, and then we'll start looking at these problems. They are very similar to what you're going to encounter in the graded homework and in the graded quiz, but some of them may be a little bit more challenging. So I'll be right back. Okay, so before we start with the problem, do any of you have any question as to how I got to this place? So if you go to the modules and just click on the Achieve link, you should be able to see it. My apologies for not showing up as an independent. Simply click on here, hyperlink. It disappears. I add it and then it disappears a few hours later. So let's take a look at this problem. These are almost like review. Oh. Is that large enough for everybody to read? Okay. So this is not today's lecture. This is previous weeks. We have four solutions. The solutions are labeled by the concentration of H+, and then you need to store them in the proper place, keeping in mind that, of course, you don't mix acids with bases. You want them in different containers. So can you tell me what would be the solution of solution 1 and how you arrive to that answer? There's more than one way, but I'll take any suggestions. Needless to say, you can always ask Google or ChatGPT or whatever, but how do we arrive to a pH from an H+ concentration? Yeah.
Is it just a negative log?
Just put the number that you are given, the 0.35 molar, the concentration. Into the equation that you just mentioned, the negative log of H+. So the pH is going to be equal to negative log of 0.35 molar and whatever that is. I actually have a calculator here somewhere, I thought. I keep forgetting that you need to put the order. So the pH is extremely acidic, right? 0.5. The problem, let's take a look at the problem. Does it say anything about? So it doesn't mention significant digits here that I can see, but I'm sure you should observe them. So you have two significant digits here, so let's put our answer with two significant digits. And I had 0.46. Now the beauty of this is that if you have this open right now with you, the numbers that you have may be different, right? Because the system scrambles the numbers. It generates new numbers for every student. So, I mean, that's a good thing, I think, because it lets you practice. So that means that the first solution needs to go into the acid container. The other three, you're going to do the same thing, but you have different numbers. Now, if you have practiced this enough, you know that this is going to give you a basic pH, right? The size of this exponent, if it's less than 10 to the negative 7, 10 to the negative 8, 10 to the negative 9, etc., is base. If it's 10 to the negative 7, is neutral. If it's larger than 10 to the negative 7, 10 to the negative 6, 10 to the negative 5, is acidic. So I'm not even going to bother with that unless the problem wants the solutions. I mean, let's see what happens. I'm just going to put solution 2 on the basic container. Let's look at solution 3. This one is also basic. And this one is going to be 1, 2, 3, 4, negative 4. So it's going to be acidic. Okay? So solution 3 basic. Solution 4 acidic. And I suppose I submit my answer. Is he going to want the answers? Oh, yeah, he wants the answers. So mark the first one correct, the other two as incorrect, but these I'm sure thinks that is right. So everybody today, after today, knows how to calculate the pH from a H+ concentration. Straightforward. Okay. Don't make me look bad when you go in a year from now to another course and they ask you the same question and you tell them that you took biochemistry and you don't know how to do it. All right. So let's go to the next problem. It's not about ego, you guys. It's about really the learning objectives. We do need to know how to do these things. So this is the same question in reverse. You need to verify the label on several stock solutions. A little bit of nomenclature here. A stock solution in biochemistry, it probably means the same as in general chemistry. It means a solution that you use to make other solutions. Is your stock, is your, what's the word, inventory. So if you want to make a certain solution of acetic acid diluted, you start with a stock solution that is more concentrated. So using the pH meter, you determine the pH, and you have it right here, and now you need to label the concentration of H+. So as you can imagine, since you gave me this equation already, what we had to do is the reverse. Now that's not the only way to do it, but if I want to get the H+ concentration, I simply take the pH and raise it to the negative, sorry, I take 10. Hi there, welcome. So we have 10 now as the base, raised to the negative pH. And you repeat that for each one of the problems. Now, I don't want to assume that everybody can do it. So can we please, as a class, if you guys don't mind, give me the answers? And that way you can corroborate. You probably have different numbers, right? In your 8.6. Yeah, they're different numbers. So you feel confident that you can do the calculation, right? I mean, I just don't want to assume anything. You're okay? All right. Okay, so let's move on to the next one then. Don't be shy, please. Sometimes your question is in somebody else's mind too. Okay, so here we're going to go back and understand how you write dissociation reactions for different chemicals. Now, I haven't looked at these questions to see what tools we need to use and how particular the system is about the grading. So bear with me as we do this together. As you know, because we did this at the very beginning of class today, hydrochloric acid is HCl. Here we have two choices for arrows. The single arrow and the one that shows you the equilibrium arrow, the reversible, if you will. So we know that this dissociates 100% because it's a strong acid. So we're going to use this arrow. I'm not sure if these ones are everything labeled, but I'm going to label it anyway. So we're going to put here, oops, that's no. H, oops, now it's gonna, how do I fix it now? Oh, there we go. H, 1 plus, no, H, no. I'm learning this as we go, you guys. I don't think I'm going to get it right. That plus looks weird. No, I give up. Mm-hmm. I'm going to keep it like that for now. I'm sure it's going to be wrong. They probably want the charges. Calculate pH of a solution, 3 times 10 to the negative 4. Oh, this is, remember what we did a couple of weeks ago. With a strong acid, it's tricky. As long as this number is not very small, smaller than 10 to the negative 7, you're fine using the equation that we have been using, pH equal negative log of. But if this number is negative 7 or greater, remember that that's impossible to calculate because you still have the water contributing H pluses. So you're going to start with the premise that your pH is going to be 6.9999 something. Okay? You remember that scenario? Okay. But in this case, it's perfectly fine to do it with the negative log of that concentration. Let's take a look at what is next. Okay, so in this case, you have a strong base and the dissociation of the strong base. I'll put that on the board just to make sure that we are all on the same page. I know that this is a chemistry review, but remember to put aqueous, because these are all aqueous solutions. You're dissociating these in water, not in vacuum. Now this is interesting though. Let's think about this one for a second. So sodium hydroxide is not a strong acid, it's a strong base. So it does not produce H+, right? You could easily, I would have, fall for the mistake that, oh, I have the concentration of 7 times 10 to the negative 5. I'm just going to go pH equals negative log of that number. That's not possible because this is the amount of OH minus. So this one we had to solve in a different way. I'll give you 2 versions and you pick the one that you want. So one way of solving this problem would be to say, okay, I don't have the concentration of H+, but I have the concentrations of OH minus. Because this is a strong base, I know that I can do that. So POH equals negative log of the concentration of OH minus, which in this case is going to be POH equals negative log of that number, 7 times 10 to the negative 5. And you're not going to be finished then. So negative, I don't even know if I know how to use this calculator. So negative log of 7 exponent negative 5. I get 4.1, 4.2 as a POH. Now, I cannot go back here and put that answer because they're asking for the pH, not the pOH. So I need to fix it. And I need to remember that pOH equals 14 minus the pH. That's one of the very first equations that we had before. So this comes from pH plus pOH equals 14. That was, or that's where that comes from. Actually, pH equals 14 minus the pOH. So it's going to be 9.8, I think. In this case. And let me just submit what I have so that we can look at the next one. So it didn't like my dissociation. Of course, I imagine that they want the +1, the -1. I just gave up on how to choose those symbols. Forgive me, please. But we did this one right. Now, any other way to solve this problem? And the answer is yes. The second approach to this would be as follows, just so that you have it on your arsenal. So we have the concentration of OH minus equals that, right? Same problem, different way of answering it. Concentration of H plus we don't know. We know the Kw equals 1.0 times 10 to the negative 14. And finally, we know that the Kw equals the product of the two ions, H plus times OH minus. So the concentration of H plus is going to be equal to the concentration of OH minus divided by the Kw. And that gives you the solution, but then you still have to use the pH equals negative log of the concentration of H plus. But we're going to get the same answer. 7 times 10 to the negative 5 divided by 1 times 10 to the negative 14. H plus equals, oh my God, 9. I hope I did it right. And then we'll use a calculator. Negative log of 7e negative 9 equal. Did I get a different number, you guys? I did? Oh yeah, I did. What? So this must be wrong. This I did it wrong. Is it 6? It should. Oh God, I don't know. But you get the point, right? I don't want to bore you with my mistakes in arithmetic. So it's 7 times 10 to the negative 5 divided by 1 times 10 to the negative 14. This comes here positive. 14 minus 5. 14 minus 5 is 9, isn't it? So why is this giving me a different answer? Did I do the calculation wrong? I'm doing something wrong in the calculator.
Is it supposed to be Kw over OH?
Say that again?
Is it supposed to be instead of OH over Kw over OH?
Oh, maybe that's what I went wrong. Yes! This comes to divide. Oh my God, that's the reason. Yes. Thank you. Okay, so this is backwards. Please erase it. If you just wrote it down, it's incorrect. So it's Kw divided by OH minus. Yeah, so this gets flipped. My bad. So we have to get the same answer. I'm going to trust that that's the case. Questions? Excuse me. Okay, let's move on to the next one. Okay, so now, quick reminder before we address this problem. From very basic concentration principles of chemistry, you have this relationship of, what is it? Concentration, initial concentration, initial volume equals final concentration, final volume. So I put 1 and 2, but initial and final work just as well. This idea of proportionality is important. If we start solving here, we're going to see that, of course, as you increase the volume, the concentration decreases. As you increase the concentration, something happens to the volume. But we need to take a look at this problem, remembering that. Let's take a look. You need to use a dilute hydrochloric acid solution in an experiment. However, the only bottle of hydrochloric acid in your lab is 5 molar. Calculate the pH of the solution you prepare by diluting 4.5 milliliters of 5 molar to a final volume of 500 milliliters. So a simple application of that equation, right? We have 2 volumes, 1 concentration. We're looking for the final concentration after you dilute it to 500 milliliters. The only thing here to remember is, and this is something that probably is not covered too much in chemistry anymore, but that is important to realize that it does exist. Did you know that there's a concentration called molal with an L at the end instead of an R? So you have molar and you have molal. Always assume in biochemistry that you're dealing with total volume, not the volume plus what you add. Does that make sense? Because it's a different thing to say, okay, I have 5 milliliters plus a liter, as to say I have a liter and I subtract 5 milliliters and then I add them back of a different solution. The result is slightly different, and that's the difference between molar and molal. In one, you take into account the thing that you are adding. In the other one, you take into account only the total volume after what you add is added. Okay, I'm going to skip this one because I think it's straightforward. I do want to get to one a little bit more challenging with Henderson-Hasselbalch. This one is a thinking problem more than a calculating problem. You can certainly do it quantitatively, but if I explain clearly the idea to you before of pKa, you should just pick the answer from here without having to solve anything. So what would you choose? Which aqueous solution has the lowest pH? Notice that all of them have the same concentration. If they didn't, then it would be a little bit more tricky. But all of them are 0.1 molar. Any suggestions? What do we look at? Or is there any relationship between the pKa and the strength of the acid? So the smaller the pKa, the stronger the acid. You go straight forward to that. This is the smallest pKa of all. Hydrofluoric acid must be the strongest acid. So all things considered the same concentration, that's going to have the lowest pH. If you have slightly different numbers, just go with that. Okay, next question. Okay, so once again, this is making sure that you understand the relationship between pKa, Ka, and acidity or alkalinity. In this case, we're just comparing weak acid to strong acid. The Ka of a strong acid is infinite, it's huge. The pKa of a strong acid is close to 0. So with that in mind, we just drag these to the different boxes. I think we all know this one goes here. So I'm not going to ask you. We just heard that the larger, the smaller the pKa, the stronger the acid. So the larger the pKa, the weaker the acid, right? So a pKa of 9 or 10 is going to be a weaker acid than a pKa of 3 or 4. But what about the Ka? So we need to be thinking differently, right? A large pKa is going to result in a small Ka. A small pKa is going to result in a large Ka. So this is probably a strong acid, right? Acetic acid is the paramount, the main biochemical acid that is used as the example of a weak acid. So I know that I need to drag that one there. If in doubt, look up the Ka or the pKa, and you're going to see that it's in the order of 10 to the minus 4, 10 to the minus 5, which would make it a weak acid. When anything dissociates partially, it's a weak acid or a weak base. When it dissociates completely, it's a strong acid. Questions? Okay. Okay. Oh, this is a challenging one. So let's do this together, because this one is going to take some steps. So you may know that vinegar is about 5% acetic acid, but here they're going a little bit more precise. So what information do we have? Well, we have the molar mass of acetic acid, we have the density of acetic acid, and we have the Ka of acetic acid. And the question is, how much acetic acid do we need to make 1.5 liters of this simulated vinegar? So where do we start? I'm going to leave that there. So let's put some of the information here on the board. Density equals mass over volume. So we're going to need that. Molar mass, typically, when you look at a formula, is grams per mole, right? So these are units of mass in grams per mole. We're given two numbers, one in density, one in molar mass. Now with the tools that we have, let's put Henderson-Hasselbalch here. And that's just a suggestion, by the way, because there's a number of ways of doing this with different degrees of precision. I mean, one thing that you should remember is that the Ka of acetic acid, which is given to us numerically, can be represented by concentrations, right? Because you have, let me put over here, CH3COOH, H plus CH3COO minus, and we have the Ka. So we know that we can actually write an equation that looks like this. And what we need to find is the amount of that plus that, right? That's the acid that we are going to be diluting. Now, pure acetic acid. So what do we know about pure acetic acid? That it has a certain Ka, that it has a molar value of 60, what was it? 60.1. Let's put the density here, 1.049. We're given a volume, bless you, a final volume of vinegar. Actually, this we can calculate very soon. And what else? We had a pH of 3. Now, looking at this formula, before we jump to Henderson-Hasselbalch, what do we know about that? What values do we know from here? I'll take any suggestions, and then we'll start. The molar concentration of that and that are going to be equal, right, in the equilibrium. So we could actually say that these two are the same, so we could actually write this, and this, bear with me while we do it this way. We could say that this is like that. Because I'm assuming that these two are the same, I can say that for the purposes of this problem, that times that is that square. So that's one approach. This value right here, the pH value, is the value of the final solution of vinegar, right? So this is this concentration. Now, if we were to look at this as Henderson-Hasselbalch, I mean, what we are looking for is how much of this we need, knowing that we have a certain amount of that and this value as a known value. Let's take that approach and then we'll look at Henderson-Hasselbalch. So we're going to solve for acetic acid and see where that takes us. So that multiplies, correct my algebra, please. I think that's what I get to. Now, numerically, we know the value of H plus from this pH. Sorry. And again, please keep an eye on my algebra. And then the Ka was given to us as 1.7 times to the negative 5. Let me do that calculation, if I can. 1 exponent negative 3 equal times 0.001 equal divided by So I actually come up with a concentration of 0.059. Okay? So this is the concentration of acetic acid that I need to make this simulated vinegar. Now, I know a volume, I know the molar mass, and I know the density. So let me put the problem back. They want a volume of acetic acid, not a mass. So that's where this is going to come into play, the density. But we have a molar concentration, which means we have a mass, right? Now, because we know the molar mass of acetic acid, we also know the grams because we know the moles. So this is written as, mole per liter. So let's calculate the moles, because we have a volume, which we can put right here, right? So if the molarity is 0.059, and we know that we have 1.5 liters of that concentration, we can actually get the moles out of that. I'm running out of space, but let me see if I can put it here. So 0.059 mole per 1 liter times 1.5 liters. So I know that from here. And that gives us what? I have to do the calculation. 0.059 times 0.088 mole. Now, how many grams of acetic acid are in 0.088 moles of acetic acid? Well, for that we have the molar mass, right? We can actually use this as a conversion factor to turn this into grams. I'm going to put it over. Do you mind if I erase part of this? Okay, so let's erase the top. So I'm going to take the molar mass, sorry, the molecular weight, and use this as a conversion factor. So I know that I have these many moles. I know that if I multiply that by the molar mass, I'm going to end up with how many grams of acetic acid I need. So times 60.1. 5.30. Now we need to use the density to convert the grams to volume, right? So we're going to take this number, 5.30 grams. We're going to look at the density, and I'm going to say, okay, I can get a conversion factor from this and say that 1 milliliter of acetic acid has a mass of 1.049. That's what the density is telling me. and my units are going to cancel out nicely. So 1.049. Now, here's a caveat. Whatever answer we get, we're going to have to verify to see if we can solve it with Henderson-Hasselbalch. Okay? So I got 5.06. Milliliters. Now here is the only, let me see. We used already the total volume to calculate the moles of acetic acid. So we have used everything that we have. We've used that. We've used that right here. We've used that. We've used that. So this is looking like probably is going to be on the right track of an answer. Now we're going to compare it to the Henderson-Hasselbalch equation, because this is asking for the proper number of significant digits, and I was a little sloppy about it. Let's see if we don't get penalized for that. So how many significant, we have 2 on the pH, 3 here, 4 there, 2 here, so 2 significant digits. 5.1 milliliters. And we're going to submit. Now it seems like it liked the answer. It worked this way. But it looks like a lot of work, right? I mean, I did say this is going to be a lengthy problem. I want you to do me a favor. Since this homework is available for multiple attempts, can you please look at this problem on your own with Henderson-Hasselbalch? I mean, it's the same idea. For Henderson-Hasselbalch, you're going to use the pKa, you're going to use the pH of 3, you're going to come up with the ratio of the acid to the base as the total, and that's going to give you the acetic acid. My guess is that this, as cumbersome as it looks, is going to be the straightforward way of solving this problem. Okay, so this was probably one of the 2 or 3 challenging questions in this assignment. Let's go to the next one. Okay, we go back to somewhat easier stuff. Not easier, but easier. I do mean easier because I think if you have been doing your reading and feel comfortable with the definition of acid and conjugate base, this is going to be not too bad. So the only thing is that I don't know how to use the tool, of course, right? But what was the conjugate base of that? Well, we had it earlier in the class as what? Can you remind me? What is H2PO4 with a -1 charge, right? Okay, let me see if I can use this. Capital H, and then I guess that to, how do I go back? See, that's what I don't know. Do I click anywhere?
Yeah, try it.
No? So do I click that again?
If you tap the arrow button to the side, it'll just move it.
The arrow button?
Yeah.
Ah, thank you. Okay, now I'm gonna be geeky here. P, O, so I go back to this one right here, right? 4, then you set the arrow. And how about the charge? Just go to this one?
And then put negative.
Say that again?
Put the exponent and then negative.
Okay.
Minus sign.
So I don't need a value?
No.
Just like that?
Yeah.
Perfect. Okay. Oh, God. A lot easier than I thought. Okay. H2CO3, what would be the conjugate base of that? So remember, you're going to be removing one proton at a time in every dissociation. Don't remove both. So this guy is going to have two Kas. One always stronger than the second one. The first one is going to be a stronger acid than the next conjugate base. So I don't want to spoil the fun, but would you agree with me that it's HCO3 minus? Okay, so I'm not even going to waste your time. So let's see. What about acetic acid? We just did it. So that would be the acetate ion, right? CH3COO minus. Now, is this one a little bit trickier? Not really. All we had to do is remove the plus sign and one hydrogen. So CH3NH2. No charge this time because the proton took that plus with it. Great. So let me just submit it and well, thank you for that lesson on how to use that tool because he did like that answer. Great. Okay, next one. Okay. So this is a Henderson-Hasselbalch straight question. Calculate the pH of a dilute solution that contains a molar ratio of sodium acetate to acetic acid of 5:1. So the key here is just to understand that this salt is the conjugate base, right? And because this is an important concept, sometimes we forget about that. We've been talking about strong acids dissociating 100%. We have talked about weak acids and weak bases dissociating partially. A salt always dissociates 100%. So if you encounter a problem in which you have CH3COO like that, so this is the negative ion, this is the positive ion. When this dissociates, it all goes to ions. None of it remains, like in the case of a weak acid, undissociated. Please keep that in mind. So we read this then, ignoring the sodium and just saying acetate. So this is the conjugate base, this is the acid. We're going to put this number, the 5 on top. We're going to put this number, the 1 on the bottom. Yes?
It does saturate, right? Salts when they dissolve.
Right, right. Yeah, that's another tricky thing about salts, the saturation of salts. So key word here, dilute, is not saturated. Okay, so Henderson-Hasselbalch. So this one becomes log of 5. They give you the pKa. I don't know the log of 5. I thought it was easy, but it's not. Well, I don't want to waste your time. Calculate the log of 5. Whatever number that is, you're going to add it to the 4.76, and that's your answer. So straight usage of Henderson-Hasselbalch. Okay, so these become just a little bit more interesting because of the fact that we're looking now at biologically active molecules. Benzoic acid is used widely as a preservative in food. Benzoic, propionic, there's a few other organic acids that are added to bread and other flour products to keep them from growing mold. So the strongly polar hydrogen bonding properties of water make it an excellent solvent for ionic species. By contrast, non-ionized, non-polar organic molecules such as benzene are relatively insoluble in water. So in principle, the aqueous solubility of any organic acid or base can be increased by converting the molecules to charged species. This is actually very interesting. I'll mention to you, and maybe we can wrap it up with that, something about the, what were they called? The tobacco trials? Tobacco trials. So I'll go back to that in a minute. For example, the solubility of benzoic acid in water is low, so this is not very soluble in water. The addition of sodium bicarbonate to a mixture of water and benzoic acid raises the pH and deprotonates the benzoic acid to the conjugate base, which is quite soluble in water. Okay, so now what do they want? So with that knowledge, they want you to take these three molecules and at these different ionic strengths or base and acid concentrations, predict where they will go. Is that what they want? Categorize the based on whether they are more soluble in aqueous solution. Okay. So you look at this and you look at the pKa. Okay, acidic pKa, meaning at a pH of 4.9 or lower, this is going to be the preferred form. At a pH of 5 or higher, this H plus is going to be gone. Okay, but at a low pH, so here, this is going to be the preferred form. This one is the opposite. This is an acid. The OH is an acid, but it's a very weak acid with a pKa of 10.1. So you have to get to all the way to pH of 10.1 for 50% of this to exist here and 50% to be the negative version where this is gone. So you would have to put it in very basic solution for this to be negatively charged and therefore be more soluble, right? This one, as you see it, is not going to be very soluble because of the OH. But without the H, with the negative charge, now it's a little bit more soluble. So that's what you're answering. This one, 3.6, at an acidic pH, this is charged, which is going to make it more soluble. If you put it under a base, if you put it here, that H plus is going to be gone, and this is going to be less soluble. So it's going to be more soluble in the acid. And that's that. So let me show you about the tobacco trials before I forget. This used to be, so when I used to teach this without the benefit of these testing platforms, I used to give students a printed exam with questions. And one of the questions in that exam had to do with nicotine and what the tobacco companies did knowingly, which was incredibly unethical, not to say illegal. I mean, I don't know if it was illegal, but it was certainly not ethical. It turns out that nicotine, let's take a look at the structure. And you're going to predict what the tobacco companies did. Okay. So what do you think would happen? Do we know the Ka? We don't need it. What do you think would happen at a very acidic pH to this structure? I mean, are these ionizable groups? So it seems to me like this could pick up a hydrogen under the proper conditions, right? So it's going to be charged. At very low pH, this is not going to be charged. So the tobacco companies knew that nicotine was more absorbable at a certain pH. And they knew the pH. So when they were under scrutiny to make a few more $1 million, what they did is that they increased the pH of tobacco by washing it in ammonia, therefore decreasing the pH and making the nicotine more absorbable by the human body. So they made people more addictive faster before they had to basically put all of these warnings that you see. So they are they're called the tobacco trials. I don't know if it's here. Huh? They used to be called big tobacco now. Well, anyway, if you are interested, just Google it. And it was just a manipulation using the knowledge of Ka that allowed these companies to make nicotine more addictive because it was absorbing better. Okay. Same thing with this one. So aspirin. The formula here is a weak acid with a pK of 3.5. Have I told you that I'm colorblind? No, I haven't mentioned that to you. So they're talking about red. I don't see that as red. I see it as maybe pink. Is it really red?
It kind of looks like.
So I confuse certain greens with browns, but I also confuse blues with purples. So sometimes I see something and like Ben is, that's a blue to me, but it may be purple. Is it purple or is it blue? Okay. Your scrubs are dark blue maybe?
Dark blue.
Yeah, but if I put the color blindness test on the board, you're not going to believe me when I tell you that I don't see nothing. I mean, I don't see anything, and you do see a number. Any other colorblind person here? No? Mostly in males because it is an X-linked allele. Anyway, so let's assume that this is red and that that's the ionizable group. So what did they say? Yeah, so this is a really great question. Knowing that the pHs in these two different organs, the stomach is 1.5 and 6 in the small intestine, and knowing that this guy has a pKa of 3.5, at 3.5, a pH of 3.5, you're going to have 50% with that H there and 50% with that H gone, right? Now, if we move this to pH of 1.5, imagine the equilibrium is right here. So I'm moving now to keeping the H plus because I'm lowering the pH. So I'm moving this to favor this. Okay? Now, I increase the pH. I move to the intestine, pH of 6. At a pH of 6, almost all of the aspirin has no hydrogen here. If this hydrogen is gone, this is a negative charge. We were told that it's more absorbable when it's charged. So I hope you can see that at a pH of 6, this is going to be mostly charged, and therefore it's going to be more absorbable. So the absorption of aspirin should take place in the small intestine. So let's choose carefully here. If you want to help me to pick an option. So we agree that the small intestine should be the answer, right? But what's the reason? The pH of the contents of the small intestine causes aspirin to be deprotonated and charged? Sounds to me like the third choice should be the right one, right? So would you agree with that choice? If you don't, I need to hear you because you may be right and I may be wrong. And we need an explanation. You don't think that's?
Yeah, I got the stomach as the correct answer.
Okay, so let's take a look. That's actually worth noting or not worthy. Let's think about this again. The polarity of the molecule determines the absorption rate, charge, and highly polar molecules pass slowly. I didn't read that part. So charge and polar absorb less likely. So I was reading it wrong. I mean, I didn't read that paragraph. I assume more soluble in water is going to be absorbed faster because it's charged. But no, it's the opposite. It's the uncharged part, the protonated part, this one, is more absorbable. So that is going to be favored in the stomach. You're absolutely right. That's why I always have to ask students. You guys know more than I do. And therefore, because of that, it's going to be not the answer that I picked, but one with the stomach and one to be protonated and uncharged. This one right here. Because the problem with this one is the stomach is the right answer, but at a low pH, the aspirin is not going to be deprotonated. It's going to be protonated. Thank you so much for that. So let's answer that. You just saved me a agonizing negative answer, whatever. Okay. I just want to take a look quickly at the others to make sure that there's nothing terribly horrible here. Okay. Now, I'm going to leave this problem for later because this problem is going to take us a half hour. And I want to take a look at the others. Match each weak acid with the pH value at which it would buffer. Okay, so this is going back to the plus minus 1 pH units or plus minus 2 pH units. So you look at the pKa, and you figure that this is going to be an okay buffer at a pH of between 3 and 1. This one between 10 and 8, so on and so forth. That's all you had to do. Okay? This one, and I still need to ask you about lab, has to do with the nonpolar length of the chain and the fact that all of them are, actually this one has multiple hydroxide groups. So these are ionizable groups that would have to be taken into consideration. So what would be your guess, and maybe you can guess this one based on the lab that hopefully by now you have completed, which I have to grade by hand, by the way, so please don't think that I'm not looking at them. I will look at them. Which of those three you think would be the most soluble in water? So if you look at the three of them, this is actually the shorter hydrocarbon chain. Not only is it shorter, which would make it more soluble, but it's also the one with the more potential hydrogen bonding probabilities or atoms. So this guy has to be the most soluble in water, right? See everybody nodding. Now, the question then is between these two, which one is going to be less soluble? Well, the longer the aliphatic chain, the hydrocarbon chain, the more insoluble it's going to be. And that's a result of doing that experiment, the virtual experiment with the cohesion. So this one has 10 carbons in addition to the methyl group. This one has 5. I would predict, and I hope you agree with me, that this would be less soluble. This would be more soluble in water. Okay. Finally, I think we have one more problem to take a look at. So this one is going to take us into like what we're going to talk about more in the next chapter in amino acids. Same thing with that problem that I didn't solve. We can always work on it when we do the amino acids next week. We're going to spend 2 weeks. Do we meet next week or not? We do. Let me take a look very quickly. Well, just look at the syllabus because we do have a couple of times where we don't meet. So you look at this structure. And let's see, suppose that for the pK is probably, okay, 3. Oh, interesting. Ah. So I'm sorry, I haven't looked at this problem and I'm just puzzled. So this one has 2 ionizable groups. This one has 2 ionizable groups, but with more hydrocarbon, and this has only 1 ionizable group. Oh, we just need to look at the charges. Never mind. I was reading it too much. So if you know that the pKa of these carboxyl groups is about 3, and you are now at pH 7, which is more basic than when these guys lose the hydrogen, the assumption would be that both of these carboxyls are going to have lost their hydrogen by the time you get to pH 7. Keep in mind, you guys, there are 2 equilibria that are different, but they roughly have the same pKa. So that one is gone, that one is gone, that is going to give you a charge of -2, right? At a pH of 7. If the pH was 3, then you would have 50% and 50%. If the pH is 1, all of it would be protonated, so the charge would be 0. So my guess is that that should be the answer. Now let's take a look at the next one. What is the net charge? Oh, but wait a minute. Yeah, -2 because there's 2 ionizable groups. So in this one we only have, no, we also have 2. So there's no difference, just the length of the chain, right? So we're going to go with the same. And finally, only 1 ionizable group. At pH 7, that hydrogen should be all gone, so it should be a -1. And then the solubility is based, of course, on the length of that hydrocarbon chain. So this should be the most soluble. Sorry, let me take a look. 4, 4, and 2. So this one should be the most soluble, the top one, then that one, and then finally the one at the bottom. Okay. I'm going to submit it partially. So we got the three dissociations correctly. I didn't bother with the last one. Okay, so lab. Any questions about lab? I know it was a little tedious, but I think it conveys the idea of, you know, hydrocarbons and water and these charged species and how they contribute to cohesion. Okay, so I'll be posting a new lab for next week, starting tomorrow or the day after tomorrow. And please, if you can take a look at that problem that I skipped, so that we can talk about it next Tuesday.